Google Cloud, and today I will be talking about TFX. Right, so there will be a bit of overlap between the talks, but not a lot, I promise. I will also be talking about pipelines. I will be focusing on the components that are required to build a pipeline. So you've seen this slide before, so the idea here is usually data scientists focus into developing the machine learning code. They focus on the problem, usually they forget about all the other components that they come to the picture when you want to move something to production. So for example, we have the machine learning code, and then we decide we spend like 30% of our time writing this code, and then we start thinking, okay, so how do I make this running 24/7, or where is my infrastructure that I want to deploy this model for training? How about configuration, and where do I do feature extraction? And also the monitoring. How does my model perform when it goes into production? Does it degrade? Is it okay? What happens when I retrain my model? Is it as good as the previous one? Is it better? Is it worse? So to answer all these, or to develop all these components, it requires to having a big technical debt. So you're either going to build them yourself, which creates debt, or you can use something like TFX. Right? So TFX is here to help. It gives you some solutions to these problems out of the box, and we're going to have a look on how this can be achieved. So a traditional pipeline, when we're talking about, of course, structured data, I'm focusing into structured data, I'm not talking about images, there are some differences there. A traditional pipeline looks like this. So you have data, probably stored into a database or files. You ingest the data, you want to do some analysis to understand your domain. You want to validate your data. Is the values that you see for the features accurate? Was there an error when you ingest the data? So you have to do that step. Then you want to transform the data. So you might want to normalize. Maybe you have like date of birth. You might want to calculate the age of someone. And then you train your model. Then you evaluate and validate the model in production and before as well. And then you serve the model. So you might want to serve the model by an API for online predictions, or you want to deploy the model into a way that can offer batch processing, batch predictions. So how can TFX help with that? So TFX is an extension of TensorFlow. Did you guys hear about TFX before? Do you know what it is? Okay, okay, so that's a great presentation then. So TFX offers solution to all these steps, and it's an open source framework. You can download it and use it, and I'm going to go through each of these steps right now. All right, so the first step was data validation. How do you do the data validation with TFX? Well, first you want to compute and visualize your data. A way to do it, you imagine that you have like data from day one. You generate the statistics using generate statistics from CSV command, for example, and then you just visualize your data. So how many of you have seen such visualization before? Okay. So what tools do you use to do it, like pandas or? Right. So yeah, I mean, it's not special, like by the looks of this slide, but it is in terms of how it works. Because usually what you do is you visualize your data, and the data fits into your laptop or into a virtual machine. However, when you use TFX, what you can do is you can analyze terabytes of data that do not physically fit into your laptop. And for that, you use techniques like distributed processing. And it's very complicated to deploy a distributed processing system, but what TFX offers you is you can just define the runner. So you can say, I want to run this in a distributed way on Dataflow, for example, and then it's done. I mean, you just initiate the job runs, you analyze terabytes of data, and you get back your feature statistics. So scalability is really important. I mean, we always say that, well, it's better to have more data than a more complicated model, because I think the answer is always in the data. So what TFX tries to do is enable you to analyze such amount of data. And keep that in mind. I mean, all the steps that we see here, the same thing applies. You can run everything at scale. So the second step you do on data validation is to create a schema out of your data. So what the schema is, basically, it's a contract of your data. It describes the data. And an example is this. So you say that this feature is a float number, and this other feature is an integer, and then I have also categorical features and strings. And what's the point of that? I mean, okay, so we create the feature, and then what? Well, the answer is you want to take the feature and use it to validate other data sets. And by the way, I forgot about this. So what you can do with the schema, you can alter the schema. So if, for example, you're analyzing categorical values and then you have a new value, you can add it. You can say that, for example, I want like the age of someone to be, it's okay if the age of someone to be missing from my data 50% of the times, but not more. So you can say, I'm accepting some change in the data when I validate. So I'm okay to have some skew in the data, but I want to have control on what that skew is. I don't want to get a data set that nobody has an age, and I'm okay if few ages are missing from the data. Okay, so you have control on creating this contract. I mean, if the first version will be out of the data, then you can modify this schema. And that's where the fun begins. So you have data that you train from day one. Sorry, that you use from day one. You generate the statistics. Probably you train the model based on this data, and then next day comes, you want to retrain the model because you have a training that happens every day. So you take the second day data, you generate the statistics, and then you compare them based on the schema, right? So you're checking if the second day is good enough to process, basically. Is it good enough to train my model, or is there a big skew in the data? So maybe I should stop, I should check the data, understand why there's, this difference. Very often we pull data from databases that we don't have control. Maybe the developer changed something in the data, maybe they deleted a column, maybe they added one. And you have to have control on this. Well, if you want to move to production. And as you can imagine, it's not just for training. You can use the schema for predictions as well. So if you are predicting every day, like the data from the previous day, then you can use the same schema almost and validate your predictions. Again, if you see that your training is very different based on what you are predicting, then your environment change and you have to take an action. I said almost the same because when you're validating your serving data, you don't have the label because that's what you want to create. That's why we define a different environment for that. Right, so the next step is data transformation with TensorFlow. Again, idea is the same. You want to transform your data to scale them from -1 to 1 or from 0 to 1. And you want to do this again at scale. So you want to do it among all your data and not just what you can feed into your laptop. Right? And another problem when you're doing the transformations, the same transformations you do before you train the model should be the same before you serve the model. Okay, so I have date of birth and calculate the age, and then I train my model. Well, if my production model receives date of birth, it won't know what to do with it, so that's not a valid input. And we have the answer for this as well. So you get the raw training data and you analyze them using TF transform. This analysis happens at scale in a distributed way again. And then you generate the transformation function, which is basically a TensorFlow graph that describes what transformation should be applied to the data. So it's like a definition and also has values like the mean of a feature and standard deviation and so on. You also create some metadata that you can use later on. It makes your life easier when you create feature columns on TensorFlow. So you take this graph and then you transform your training data, and there you have them. And you do the same for the test data. You transform them based on this graph, and you have the transform test data, and then you train your model. But then the problem is, okay, so now I transform the data and I train the model. In production, I won't have transformed data, so how do I add this step? And basically the answer is here. So you can take the same graph that you use here, and TensorFlow allows you to, when you export the model, allows you to embed this graph into your saved model. So basically, the output file you get after training can also do the transformation, and therefore, you don't need to worry about it. Also, usually this is a big headache, not with TensorFlow. Very quickly, some transformations you can make is, like the values from, changing from 0 to 1, Z transformations, strings, so n-grams and splitting strings, creating packets, feature crossing, and also applying a different model as part of the transformation. So you might have a model that predicts something and you want to use that into your data, or changes something in some features, and you can embed that. All right, so, and then we have the training part, which I talked a bit about it, but I want to say more about how you train on TensorFlow. I'm focusing to the pipeline, so forget about it. Let's move on. So, model analysis. So now you train the model and you want to understand the model. Okay, so how do you do that? Well, we have another package, which is TensorFlow model analysis. And what you can do is, when you train your model, you just export a second model which is specific to model analysis. So you add this snippet into your code, and then you run model analysis. And this can give you metrics like, well, what's the overall accuracy of the model, of course, standard metrics. But the most interesting one is slicing. So I know how my model performs, like overall. So I know it's a very accurate model. But then how does it perform between different parts of my data? So is my model accurate enough when I compare male and female, or is there like a bias in the model? Or what happens when I see different times in the day? Like, are there times with much less accuracy? So, and what can you do about it? Maybe you decide that, well, you don't have enough data for a specific time, and then you go ahead and collect more data so that this skew in the predictions does not appear. And I find these very, very powerful. I think it's good to understand the data. You can also understand where the model fails to perform really well, and then you can go back and fix this error. Of course, you can plot stuff. Again, nothing complicated there. And this is the other part that I really like. So it can compare different models. So you can have a history of the 5, 6, 7 previous models that you trained, and then you see how the accuracy differs per model, and then you can take an action. So if the new model is not better than the previous one, then don't push it to production. If it's better, then go ahead. All right, and then serving. So, well, I have the model, I did my model analysis, I'm confident with the model. How do I push it into production? Well, we have a service which you can run a command, point it to where your model lives, and that will basically start the service. If you hit the endpoint, it will give you back. If you hit the point, it will give you back the predictions. The default here is with Google Remote Procedure Calls, super fast. It's not the norm, I know. Therefore, we also have a RESTful API which you can use to do the same. Okay, so different steps. I think the question now is how well does this run? I mean, all I said about now was, like writing the code and we have a library and everything is great. But when you want to run it, I said, well, you can write it in a distributed way. And on Google Cloud, we have different products that you can use for each of these different steps. The most important here is TensorFlow, that, as you can see, is used among the most of this process. TensorFlow is based on Apache Beam, so it's a framework that you define a job, and then when you run it, you say, I want it to run on TensorFlow, or I want this to run on Spark, and it will initiate the job. And it's good. TensorFlow, it's a managed service, so you don't need to worry how it starts, how it finishes, how it scales. All this is abstracted from you. BigQuery is our database it's data warehouse solution. You can do analytics, scales really well. For training, again, you can run training at scale. So we have a service that you submit your model and then it will train on your data. You just specify the data path and that training can happen at scale. So TensorFlow supports distributed training, supports GPUs and TPUs, so you can just submit a job that can run on 8 machines, 10 machines, that's not a problem. All right, but how do you connect all these steps? I mean, we're talking about the pipeline, but then, you have to link them together. So you can use Composer, which again is Apache Airflow, which can basically transition from one step to another, initiate these jobs. And also you can use more complicated solutions. We talked about Kubeflow pipelines earlier. It's a great solution. It's quite new. I think it will become the standard. So go ahead and have a look at it. Again, depending on your technical expertise and your needs, you might choose one or the other. So that's it.